Hello, my calculus doing friends. Today we're going to look at the definite integral, and it's 4.2 in your textbook. So we had looked at a Riemann sum, and you remember that the Riemann sum gives you the net area, and so it gives you the area that's trapped between the curve and the x-axis. And so if it's above the x-axis, the Riemann sum would count that as positive because it's counting, it's using the function and how high the function is, and so this would be a positive value. Whereas if it's below the x-axis, because it's using the function, your function would have a negative value, and so this would be counted as negative. And so it's possible for your definite integral, which is going to give you the net area, to give you even a negative area or zero area. So it gives you the area that's trapped between the x-axis and the curve. So this was some notation that we had for Riemann sum. They said that we wanted to sum up, we wanted to add up the height times the width, and if we wanted to let the width go to 0, and so that we had a whole bunch of rectangles, then you could go from 1 to n and let n go to infinity. And this would give us infinitely many rectangles is what that would do. So our little rectangles in here, they'd have width nearly 0 under this, and there would be infinitely many rectangles, and that should give us a really good estimate. So switching that notation up again, remember that delta x is equal to b minus a over n, and switching that notation up for integral notation, this symbol right here, it might not look like it, but it's a big S is what it is, and what that big S is for is add up, sum them up, and we're going to sum up from A to B. We're going to go from A to B and sum up the heights times the widths, and so the dx stands for the widths, and then this is called the lower bound, and that's the upper bound, and this is going to give us the area. So it's the height of each rectangle times the width, and we're going to have infinitely many rectangles. And just to reiterate, it's possible for this to be positive or 0 or negative. So on this picture over here, it looks like it would be positive because there's more above the x-axis than below, more area above than below. And so anyway, so we'll give a try to sum here. This is problem 34 out of your book, and they're asking us to find the integral, which is going to calculate the area under the curve trapped by the x-axis and the curve from 0 to 2. So here's 1 and here's 2, and we're going to find this area here. So this is the area that we're wanting to find, and you notice that that is a triangle, so we can use the area for a triangle to find that area. So the area of a triangle is half the base times the height, and our base is 2, and our height is 4. So when the dust clears, this is 4. And so we did a lovely job on that. And then it says for us to find the area here, so the integral from 2 to 6, and that's going to be the area trapped by the curve and the x-axis. And so here's 6 right here. And I notice this is 3, not that I care, and that's 5, not that I care that much on that. This is the area that I'll be finding, the area trapped by the curve and the x-axis. And because it's below the x-axis, it will be negative. So I already know it's negative. And since this is half a circle, right, so the area of a circle is pi r squared, and the area of half a circle, right, so half, right, a circle So that's the area of a circle. The area of half a circle would be pi r squared divided by 2, right? And so our radius here, so here's the center, and our radius goes from the center to a side. So the radius, it would be hard to count it here, but it would be the same, but it's easy to count here or to count it here. Our radius is 2. So for half a circle is pi r squared over 2. And coincidentally, we have a radius of 2, so this is pi 2 squared over 2. Lost my negative, but there's my negative back. And so that's 4 over 2, which is 2. So this is negative 2 pi. And so we did a lovely job on that one. And then from 0 to 7, and so, and what you can do is you can find the area of the pieces and kind of put them together. So we know that this area here was 2 pi, and then this area here was 4. And then this area here is half 1 times 1, so half. And so the area from 0 to 7 would be from 0 to 2 is 4. And then from 2 to 6 is, and it's below the x-axis, so minus 2 pi. And then plus half. So 4 plus half is 4.5. And they might write that minus 2 pi. And they might write that in the back of the book as 9 over 2. I'm not exactly sure if they did, or 4.5 is okay. And so we did a lovely job on that. And then they're asking us to find from 2 to 4, part D here. So here's from 2 to 4. And so that's a quarter of a circle. And I already knew that half of the circle was 2 pi. And so it's half of a circle, and it's below, so it's negative. So this is going to be negative 2 pi divided by 2. So this is negative pi. And so we did a lovely job at that. And so there we have that. Okay, so on the second page of the definite integral, it has all these properties and of the integrals and just kind of the basics there. And you're free to go and read them all in your book. I think it's a good idea to do so. I think it's kind of fun to read the book. Paid a lot of money for it. So anyway, let f and g be integratable functions on the interval that it contains a, b, and c. And so they said the integral of f of x dx from a to a equals 0. And I just put over here just a little justification, either a picture or something, just to show you why. But if my interval goes from a to a, I mean, think about that on a picture. And so here's my curve f, and here's where a is, and I'm going to ask you what's the area basically of that line, right? And it's 0. And so more reasons for it if you wanted. Remember that your delta x is your upper bound minus your lower bound divided by n. And if your upper bound and your lower bound are exactly the same, a to minus a is 0. And then this property is so that you can adjust your upper and your lower bound. So notice here that they have b to a. When we're used to having a to b, and they say that that's equal to, and then you can switch it, minus of a to b. And if you're like, oh, when would I want to do that? I'm going to show you some problems when you would want to do that here in a second. But just so that you can see how that it would go. So if you switch the upper and the lower bound, then delta x would change from being a minus delta x from a minus b divided by n to, and then if you switched it around, right, and you factored out a negative 1 here, negative 1 times b minus a over n. And so that is the reason for the negative here, right? So this one went with this, and negative 1 times that one, right? Okay, and then the constant dx, and so if you're trying to find the constant, here's a picture that they have. Remember that I have the area under the curve is what I'm trying to find, right, when I take the integral, so from a to b, and so this has a height of c, right, and then times how long this is, which is b minus a. So all of the properties that they give you in there for integrals, you can read about, well, why, you know, and it really does make sense. And then the constant, so oops, right here, I was on here. A constant times your function, you can hold the constant still and take the integral of the pieces. We saw that with the derivative and also the antiderivative when we were looking at those. And so the integral here from a to b of f of x plus g of x, you can break it apart. And we saw that with derivatives again and antiderivatives. And then here's a special property, and it totally makes sense when you look at this picture, that if you're looking at the integral, which remember is the area under the curve from a to b, so this area from a to b, this whole thing, then a to c, so the area from a to c, plus from c to b. And so, yeah, certainly if I add those two up, I would have the whole thing. So, okay, so we're going to look at using these properties here. I might even put these properties upwards so that I can see them over here so that we can use them. Okay, so this is problem 42 from your book. It says given that, and then we have the integral of sine x raised to the fourth, right, dx from 0 to pi is equal to 3/8 pi. And then they ask us to find what is from pi to 0 of sine raised to the fourth of theta d theta. And the deal is that this theta here is a dummy variable, x is a dummy variable, and so you could change it. So this is exactly the same as pi to 0 of sine to the fourth x dx. And so these are the same. And we don't know how to find integrals yet. We're going to learn that. That's something that we're going to learn. And I wouldn't have the, I wouldn't want to draw this, and well, I probably could draw this, and try to figure out what this is. So it's nice that they gave it to us. Later on, we're going to be able to figure out how to find these things, and so that's coming. Right now, they're just trying to get us practicing our properties, is what they're trying to get us to do. So my thought is, well, I know from 0 to pi, and this is opposite of that, so I'm going to say this is minus of, and use that negative property of this. Lost my angle, my x there. I had to change where my office is, and so I've lost all kinds of stuff. I'm having difficulty. And then the good news is that this was given, right? They told us that was 3/8 pi, so then this is equal to negative 3/8 pi. So we did a lovely job on that. This is problem 48. It goes from 2 to 8 of f of x dx is equal to 7.3, and also from 2 to 4 of f of x dx is equal to 5.9, and they want us to find the integral from 4 to 8 is what they're wanting us to find. And I can kind of look and piece this together. I have 2 to 8, that's the biggest, 2 to 4, and 4 to 8. And so using that property, this property here, right, this last property here, I can say that the integral from 2 to 4 of f of x dx plus the integral from 4 to 8 of f of x dx equals the integral from 2 to 8, so from 2 to 8, see how it stops at 4 there, of f of x dx. Now, they wanted me to find 4 to 8, so that's what's unknown. So this one right here is the one that's unknown. And it could be any of the three are unknown. But this one is equal to 7, oh no it wasn't, 5.9 plus the unknown, equals 7.3, 2 to 8. And so I could take away 5.9 from both sides, and then I would know what that integral is from 4 to 8. So 7.3 take away 5.9, and I would be all set up. My calculator, of course, wants everything as a fraction. I decided I wanted it as a decimal this time, so 1.4. Okay, so we did a lovely job on that. And then I have an example here. It's asking us, it says that the integral of f of x dx from 1 to 4 equals 8, and then they asked us to find from 1 to 4 of negative 3 f of x dx. So that negative 3 is a constant, and I can use the constant multiple rule here, this one right here, the constant, and I can pull that constant out in the front. And so I'm going to do that. So this is negative 3 from 1 to 4 of f of x dx. And then the good news is I do know what that is. That was given to be 8, so this is negative 3 times 8, which is negative 24. Okay, so that's that section. Oh, there's one more page, and we'll give a try to it. Okay, so they're asking us to find the integral from negative 5 to 5 of x minus the square root of 25 minus x squared dx. And they're giving us a hint, hey, think about area. So I'm going to break this into two pieces because I know what that looks like to draw it, and I actually know what that looks like to draw it, but to look at the whole thing together and draw it, I'm not exactly sure. And I'm using that property of integrals that said that if you have two functions and you're subtracting them, that you can subtract the integrals, right? So I'm going to have from negative 5 to 5 of x dx minus, and then the integral from negative 5 to 5 of the square root of 25 minus x squared dx. So I know what y equals x looks like. It looks like this. And here's where 5 is. And here's where negative 5 is, the same distance here. And would you guys agree with me that this area here from negative 5 to 0, and it's underneath the curve, and it's a triangle, and I could find it. And this area here from 0 to 5 is the same. And so this must be 0. Now, if they would have, I would have been able to find it if they would have said negative 3 to 2. I still would have been able to find it of this because this is a triangle and I can actually find the area of it, and that's a triangle and I can actually find the area of it. But because these two triangles are exactly the same size, this part is 0. And then I want to think about, well, what does this one look like? Y equals the square root of 25 minus x squared. And I hope that you recognize that as half a circle from our Math 1 days, pre-calculus days. So if I'm going to draw this, so when I'm at negative 5, this is actually 0. square root of 0. When I'm at 0, this is actually the square root of 25, which is 5, so it's up here at 5. And then over here I'm at 5 as well. If I put in 5, I get the square root of 0. And this is actually a semicircle, right? It's half a circle there. And so I'm supposed to, I'm going to bring my minus down here before I lose it. So now I'm looking at, well, what is this integral from negative 5 to 5? So it's this area that's between the x-axis and the curve, and I know that that the area of a circle is pi r squared, and this is half a circle, so this area is pi r squared over 2 because it's half a circle, and I know that my radius is 5, so this is pi 5 squared over 2. So this is minus 25 pi over 2. And so that's what that integral is. Okay, so we did a pretty good job on that, and so that's 4.2, and we'll also have Zoom questioning. We had Zoom questioning today from 11:10 to whatever time. So questions, your guys' questions. Okay, bye-bye.